Okay, so I want to go over example 1 from lecture 5. So what we have here in this problem is we have some sort of mass which is connected to some axis of rotation, right? So if you recall from the last lecture, we're able to calculate the torque which is applied to an object as it rotates around some center axis of rotation, as long as we can find a couple things. So what we need to do is we need to find what is the position vector for each of these forces which are applied. So there's a force applied here, a force applied here, and a force applied here. Each one of them is going to produce their own torques on this object which can freely rotate. So let's find the first position vector. So we go from the axis of rotation, and that's where the tail of the vector starts, and we go to the head of the vector, which will be where the force is applied. So we'll call this R2, and we'll call that R2 because it's associated with force 2. Now if we look at force 1, which is a little further down, we would have another vector which would go in the same direction as R2, just a little bit longer, and we'll call that R1. And that's where force 1 is applied to the object. And then we have the third force, which is applied to the object right there, and we'll call that R3. So now we have 3 position vectors, and we have 3 forces. So let's recall, the equation for torque is equal to the magnitude of a position vector, the magnitude of the force, and then sine of the angle between the two, where the angle between the two is going from the position vector to the force. Now, if you remember the right-hand rule from physics, when you curl from one vector to another vector, that's going to be the direction in which the resultant is. So if we curl, let's imagine that we have a position vector like this, and we have a force vector like this, and we curl from R to F, that means the resultant will go outwards, right? So the torque will be generated out of the board. So we're going to use that fact to find out in which direction the torque is applied. So if we always draw this so that R is curling towards F in the counterclockwise direction, the torque will always be directed out of the board if the torque is positive, but if it's negative, it will be into the board. So let's try and calculate each of the torques, and then we can find the total torque. So the total torque will be equal to torque 1 plus torque 2 plus torque 3. So let's look at torque 1 first. So for torque 1, we need to find the magnitude of position vector 1, the magnitude of force 1, and sine of theta 1, where theta 1 is the angle between them. Well, theta 1 can be calculated by plotting the 2 vectors. So notice that the position vector is directed straight downwards. So we'll draw that vector like this, and we'll call that R1. And then we can also see that if we have 2 units of distance from the axis of rotation to where F2 is applied, and then another 2 units from F2 to where F1 is applied, then R1 is equal to 4D, or 4 units of distance. And then we can see we'll put both the vectors at the same point. We'll put their tails together, and that will help us calculate the angle. We can see that the force is directed straight up, and it has a force of 4F units. 5F units. Okay, but here's the thing. Let's take the angle here. We're going to go from R to F, and you can see we go all the way in a straight line. So theta 1 is equal to 180 degrees. So it's obvious from that whenever we put that into this equation, we have 4D 5F times sine of 180 degrees, and that's equal to 0. Right? So we have no torque applied, even though we have a force of 5F applied at this point. Okay, so let's calculate torque number 2 and then torque number 3. So torque number 2, R2, F2, sine of theta 2. Well, to get theta 2, let's plot R2 and F2 on the same plot. Well, again, R2 is directed straight down like this. That's R2, and we can see that the magnitude of it is equal to 2 units of distance. But then we can see that F is pointed in this direction. So let's plot that with its tail at the same place. And then we'll say F2 is equal to 4 F units. Now we can clearly see that the angle between these two is equal to 90 degrees. Okay? So evaluating for torque 2, we get that R2 is equal to 2D. F2 is equal to 4F. And then we have sine of theta 2, which is 90 degrees. So it's clear from this equation that we have 8dF. And because torque is a vector, we need to give it a direction. And as we said before, when we curl using the right hand rule, curl in the counterclockwise direction is going to be going out of the board. So we have positive 8 out of the board. Now for torque number 3. Magnitude R3, magnitude F3, sine of theta 3. Well, we can see here that theta 3 can be found by putting the vectors with their tails at the same position as we did in the previous 2 calculations. So F3 is going back this way, and F3 is equal to 6F. And we can see that R3 is directed in this direction, and we notice that it has a length of 5D. Now the question is, how do we find the angle between them? And we have to use some geometry to do that. So we can see that we have some triangles here and some segments. So what we're going to do is we'll draw a dotted line going out this way. And this way we know that we have 180 degrees because we have a straight line. We know that a straight line is equal to 180 degrees. But then the question is, what is the rest of the angle defined by? Well, as you can see from this equation right here, we have a horizontal distance of 3D from the axis of rotation all the way to where the force is applied in the horizontal direction. So from here to here, we can call this distance 3D. And then if we draw another line like this, we can see that we have a right triangle. Using the Pythagorean theorem, this is obviously a 3, 4, 5 triangle. So this distance here would be 4D. So the angle that we're looking for right here is this angle. I'll give it another angle. We'll call that alpha. Okay. That's probably not a good angle to use with torque. Let's call that gamma. Okay. So to find gamma, we can clearly see that the tangent of gamma is equal to the opposite divided by the adjacent, right? So then gamma is equal to the inverse tangent of 4/3. That gives us an angle of 53.13 degrees. So the angle theta 3 in this case would be the sum of both. 180 degrees plus 53.13 degrees. This gives us a total angle of 233.13 degrees. So torque 3 can be calculated as R3, which was equal to 5D, times F3, which was equal to 6F, times the sine of 233.13 degrees. Now when you calculate that, you'll notice that you get negative 24D times F. So what does this mean? This means one of two things. It means that we have a magnitude of 24, and the negative sign means that it's actually going into the board, because we use the right-hand rule going from R to F. Another way to have calculated this problem is to take the cross product of R with F using the smallest angle and curling this way. So we could have actually used this angle as our angle and took the cross product in the other way. In either case, you're going to calculate the same magnitude in the same direction for torque. So next, to get the total torque, we have to sum them up. I'm going to write this, or 24 into the board. To get the total, we'll sum T1 plus T2 plus T3, or tau I should say, and that gives us 0 plus 8 dF minus 24 dF, and we get minus 16 dF, or 16 dF into the board.